Hi, I'll be talking about another project from the fire simulation, but this talk should have been arranged yesterday. It's about the escape fraction of ionizing photon from high-redshift galaxies and related to reionization. But I don't know why it has been scheduled today. From galaxy modeling perspective, the escape fraction was defined as the ionizing photons that escape to the IGM, or outside the via radius, divided by the intrinsic ionizing photons produced by all stars in the galaxy. As we have a lot of discussion yesterday, this quantity is poorly understood. What we have done is using a suite of high-resolution cosmological zoom-in simulations using the Gizmo PSPH code. The resolution, the mass resolution, it's around from 20 solar masses to 1,000 solar masses for the most massive galaxies. And the spatial resolution is from sub-parsec to a few parsec scale. All the simulations were run down to redshift 5 or 5-ish, and we focused our analysis from redshift 11 to redshift 6. This kind of model include explicit star formation and feedback models. Star formation takes place in molecular, self-gravitating, and dense regions. And we include feedback model, including the photon ionization, radiation pressure, and supernovae, etc. We're using standard stellar population model from Starburst 99 with the lowest metallicity track from the Starburst 99 model we can achieve. And then we post-processing all the simulations with radiative transfer code, a modified version of Sedona, which Dan Kaysen works on a lot on this. First, it's a sanity check of galaxy properties with all the simulations we got. This is the mass metallicity, this is the stellar mass, halo mass relation for this suite of simulations at redshift 6, 7, 8, and roughly 10. So we compare this with the abundance matching result from Peter Bruzzi's work and the main suite of the fire simulation at redshift 6, and we get pretty good agreement across all the redshifts. And then this is the UV magnitude of all the simulated galaxy we have at different redshifts. So this is the abundance matching from one of the, I think is Claude Andre Fauchiguer's paper, and roughly covers the UV magnitude from -19 to -10, which we believe is the dominant source of reionization, at least we believe by some people. This is the star formation rate versus stellar mass for the simulated galaxy. It does not really overlap with observations, but it's kind of lie on the extrapolation from the observational relation. So then after processing, what is the escape fraction we got? So we see the star formation rate is kind of bursty, but on small time scale. But if you average over, say, 100 million year time scale, the star formation is more stable. And the escape fraction also see the same feature. On small time scale, it varies dramatically between 0 to like 20%. But if you average the escape fraction, by averaging the ionizing photon escaped divided by the total photon produced in galaxy, that kind of averaging. For most of the time, the escape fraction is roughly below 5%. Also, we test if we average over, say, redshift from 11 to 5.5, the time average escape fraction is roughly 5% or even below that for all of the simulations we got, from halo masses 10 to the 9 solar masses to 10 to 11 solar masses at redshift 6. Then we look at the mass mass and redshift dependent of the escape fraction from our simulated sample, we basically find there's no clear stellar mass or redshift dependence from this sample, but I should emphasize this is redshift 11 to redshift 6, and halo masses from 10 to the 9 to 10 to the 11 solar masses. Then why the escape fraction is so low, so we look at the ISM structure around star particles of different ages in our simulations. So the left panel, it's the ISM structure around a star particle of 1 million year. And it is 5 million year and 4 million year. Usually, the young star particles are always embedded in very dense regions. And when it further evolves to, say, over 3 million year old, a large fraction of the line of sight has been cleared by stellar feedback, and the star particle can have our unity escape fraction. And for all stellar populations, they always sit in the ambient ISM. But if you look at the ionizing photon budget from standard stellar population models given by Starburst 99, 3 or 4 million years is roughly the time scale when the ionizing photon produced by the stellar population start to decrease. So that is the explanation why we get low escape fraction from our simulations. Then from this, I should emphasize it is crucial to have realistic star formation and feedback model to see how the ISM structure change. Then we know some of the earlier work of the escape fraction tend to have like 40 or even 100% escape fraction from some old simulations. So we have a test on the star formation model we have. The standard fire model we have, it's assuming all star formation takes place in molecular self-gravitating gas and above 100 particle per cc density with 100% efficiency per free fall time and no star formation elsewhere. We designed a model that mimics some of the low resolution subgrid star formation model that used in some old simulations and used by other people. We allow 2% efficiency per free fall time in all the gas above some density, very low density threshold, so that we allow star formation to take place in the diffuse ISM. So that is what we got. For the standard fire simulation, we got, as we have already seen, the average escape fraction, it's roughly 5% level. But for the low resolution subgrid model we intend to mimic, we got like 30% or even above. So this is a caveat for some of the subgrid model used in low-res simulations. They may tend to over-predict escape fraction largely. And the other discussion is how well or how bad we can understand the stellar population model. So we use 3 different stellar population models. This is the intrinsic ionizing photon budget produced by a stellar population versus the age of the stellar population. We look at the 2 models from Starburst 99. One is the lowest metallicity track that we use, the black line that we use in our diffuse really transfer calculation, and the model from a solar metallicity track from Starburst 99. And then we design a toy model that we aim to account for the some of the new stellar population model, including rotation or binary interaction. In this toy model, the intrinsic ionizing photon budget stays the state constant for the first 10 million years and then drops to 0. The result we got is from these 3 From these three models, we get the escape fraction very different. The model with the highest intrinsic ionizing photon budget between 3 and 10 million years has the highest escape fraction. So this is the caveat at how we understand the stereo population model. So this work has some implication on reionization. If we still believe bright galaxies dominate reionization, then where the ionized photon comes from? One possibility is runaway stars. We have, in this work, we also do a toy model of the runaway star, but do not find very significant difference. But it's only a post-processing toy model, but for self-consistent and more careful model, we should refer to other work. And if we need better stereo population model, including some of the rotation or Banner interaction, which believed to be common in stereo populations, if the source dominant reionization is not the bright galaxies, what might be? Some kind of the mini halos that suggested by John West's simulations, with virial mass below 10 to the 8 solar masses, which have order unity escape fraction. That might be a possibility, and also the QSOs as we saw yesterday. I've left my summary here.
Okay, thanks. Questions back here?
You go first.
All right. So I wanted to comment on the possibility of getting more ionizing photons out of the older stars and that increasing the escape fraction. The comment is, unless there's something fundamentally different about the high-redshift galaxies than the local ones, and it's not obvious why there would be, I think it's hard for that to be a more than factor of 2 level effect. And the reason is, in local galaxies, you can try and compare ionization-based star formation rate indicators to other types of star formation rate indicators. And, there are a factor of 2 level differences, but not order of magnitude. But if the escape fraction were way higher because of older stars, if the time integrated escape fraction were way higher, there would be a much larger discrepancy. So that suggests, to me at least, that it's hard to appeal to that as a solution.
Okay. Good to know.
I had 2 questions. One was, how do you time average the escape fraction? Are you doing a simple average, or do you do a luminosity weighted?
Yeah, luminosity weighted.
You do a luminosity weighted escape fraction. Okay, that answers one of my questions. The other was, in your comparison with some previous work where the resolution was somewhat lower, or quite a bit lower, you seem to imply that in those cases, and I think it's not a universal result, but in some of the cases that you showed, the escape fraction was high. How much detailed structure near the star particle or the region of star formation do you actually need? Because what you showed, around the star particle, it's very difficult to see it smoothed. But there's not a lot of detailed structure there, whereas we know the interstellar medium in many galaxies is very complex. So how much does the unresolved structure near, the sites of star formation in your simulations, what level of effect do you think that will have?
Yeah, there's 2 from the standard star formation model that have different resolutions. This is the same resolution, but the same simulation, but with different resolutions. One is,
so you think the resolution is good enough?
Yeah.
You do.
One of them, the highest resolution, have 100 solar masses resolution.
That's
in baronic map.
Okay.
Yeah.
Compared to